All right, so welcome people. My name is Bill Simpson. I'm from the University of Alaska Fairbanks here in town and a part of the Alaskan Layered Pollution and Chemical Analysis, or ALPACA project. And today we're going to have a virtual tour of our downtown field site. This is really a very large project, and we had a tour 2 weeks ago of the house site where we were studying indoor and outdoor air at a house. You can look on the fairair.community.uaf.edu website and see a recording of that event if you're interested in it. We'll also be recording this event, so you can take a look at it later. So today we have an exciting program with a lot of people telling you about their instruments. So I'm going to now introduce my colleague, Professor Jinshu Mao, who's also at UAF, who's going to give you an overview of what's going on at the downtown site.
Okay. All right. Thank you, everyone. It's my great pleasure to present you this virtual tour of ALPACA CTC site. This is indeed, as Bill said, it's a very large collaboration. As you can see, I'm putting lots of logos here. First of all, I should thank lots of federal agencies and international agencies for funding this effort, including National Science Foundation, NOAA, and as you can see, lots of universities. And also, I want to point out one unique part of this campaign. We have very substantial international participation. As you can see, the bottom two rows are from international colleagues, including colleagues from France, from UK, from Switzerland, from Italy, and other from Finland. So actually, so far we have 80 participants. Among them, 30 are international. So this is a really, really large international collaboration. It's my great pleasure to show you that what's happening at CTC site. So I will give you a very brief introduction of what we're thinking of, how we design for this site. First of all, then probably you have heard lots of sites. I just want to point to you that where we are, this is the Fairbanks map. As you can see that we are a CTC site at downtown Fairbanks, and we also have other sites, which probably you will hear from our folks. And we also going to talk a little bit about this Long Pass Goas. This is another site cover actually quite a bit of area. So this is something we'll be talking about today. Probably you guys already heard something about this house site 2 weeks ago. So why are we interested in what are we interested in at CTC site? So we are interested in a couple main questions. First of all, here I'm just showing you there are many pollution sources from Fairbanks, including power plants, including house heating, including truck, cars, and even snowmobile and the wood burning. So there are many sources, but which one is really driving the Fairbanks pollution, or which sources? This is something we are really interested, but we can only measure at a few locations. Here is what we are measuring at the CTC site. We're measuring very extensive chemical composition, and from what we are measuring, we're trying to derive the source from each source strands from each of these sources. And here we are using this kind of fingerprints. So the main question we're trying to answer is which sources account for a majority of Fairbanks PM 2.5. Another question is that do burn bans really work in Fairbanks? This is something we're interested. And another question we are trying to answer is that, as a matter of fact, I'm showing you here that I'm showing you this different color circles representing different pollutants from different sources, but they are not necessarily going to stay the same form throughout their life cycle. So actually, they are going to go through some chemical transformation. And as I'm showing you here, some color has changed. Also, the small circles become larger circles, which means the particles can grow. And how exactly does this happen, particularly at this cold and dark condition? This is something we are interested in. So our main question here is that how are these primary pollutants from different sources are converted into secondary pollutants in this cold and dark condition? This is something we want to understand. Also, another related question is that should we use the low sulfur heating oil to reduce Fairbanks pollution? Why do we care so much about sulfur? This is another related question. And my third scientific question is related to the vertical distribution of air pollution. Probably a lot of folks have heard about this inversion layer, and how exactly are pollutants vertically distributed among different vertical layers? This is something we really care about. For example, where are pollutants located? And we know there are lots of pollutants in surface air pollution, but do power plant emissions really affect surface air pollution? Should we try to reduce power plant emissions? This is something we also care very much about. So this is a third main scientific question we want to answer from this site. At this point, I will maybe turn the floor to Bill. Bill, maybe you want to start to have colleagues do the talk about their instrument. I will start to do the site tour on my end.
Yes, thanks very much for the introduction to the site. And so we're going to go through a number of presentations now by the principal investigators or postdocs or students who are working with the instruments in this project. And they're going to tell you a little bit about what they're doing, as Jinshu will go around and show you the instruments that they're using. And the first person that we're going to have talk is going to be Jack Dibb, who is going to be talking about measurements of snow and also particles. Is Jack online?
I am indeed.
Awesome.
All right. Hi, everyone. My name is Jack Dibb. I'm from the University of New Hampshire. And at the CTC site, I don't know if Jinju is showing you, but it's pretty boring. I have a pump and a flow meter inside the building, and outside connected to a hose, there's a filter above the roof. And so multiple times a day, I go down to CTC and just change the filter. And then once a day, or sometimes more often, but mostly once a day, I go over to the NCORS site, which you may or may not hear more about today, but it's just across the river, about a quarter mile away from CTC, and sample the surface layer of snow. And I'm part of a group who's very interested in the chemistry determining the partitioning of sulfur and nitrogen compounds in Fairbanks. And the reason we're interested in the snow is that one way that you can clean up the pollution is deposit the material to the snow. So I want to look to see if the pollution is falling in the snow. But some of the things that we measure can actually go in the snow and then come back out and be in the atmosphere and be a pollutant a second time around. So that's what I'm up to. And I run up, after I do that sampling every morning, I spend a lot of time in the lab up at campus in the chemistry building doing the analysis in real time, because we're looking at some compounds that are very unstable and we're not sure you can ship them around the world to analyze them back at home. So that's all I have for now, Bill.
Very much, Jack. So the next person who's going to speak is going to be Vanessa, and Vanessa is going to be telling us about light absorbing particles. So Jinshu is going to be walking back inside to show her instrument.
Hey everybody, as Bill said, my name is Vanessa. I'm a postdoc from the University of Montana. And it's been really awesome to be here in Fairbanks to be part of this study. Thank you guys so much for having us here. It's been an honor. As Jinshu mentioned at the beginning, there are lots of different sources of particles and emissions that are being emitted in Fairbanks. And what our instrument does, the Photoacoustic Extinctionometer is the full name of it, or we just call it the PAX. What it does is it basically measures how the emissions and how those particulates are interacting with light, and then how that interaction with light is occurring, whether or not they're scattering that light, whether or not they're absorbing that light, kind of gives us an idea of the kind of particle and almost sort of where it's being sourced. In addition to that, getting an idea of how the particle or how the emissions interact with light also allows us to derive some things called aerosol optical properties. And those optical properties, which again is just a fancy word for saying how the particles interact with light. Once we derive those values, we're able to put them in climate models and then also get kind of an idea for what the visibility is going to look like, and then what kind of pollution is also there. So that's our instrument. And like I said, we're really happy to be here and honored to be doing science in your community. It's been great.
Thanks, Vanessa. So the next instrument is the next down the bench right here. And James Campbell, who's a graduate student here at UAF, is going to tell us about formaldehyde measurements.
Okay. Hi, I'm James. I'm working with two formaldehyde instruments right now. The first one is called COFFEE, which stands for Compact Formaldehyde Fluorescence Experiment. It uses a UV laser to excite formaldehyde molecules and other molecules that go into the sampler typically scatter the light, but formaldehyde fluoresces in the UV range and emits a blue light, and we can use that to measure the concentration of formaldehyde. This COFFEE instrument, which I guess I should point out, it's the goldish one. Yeah, thanks. It's that one. It's more sensitive to formaldehyde than the other instrument, which is that black box. But it's not as good for running for long periods of time. The second one, which is called ARIS, I don't think it stands for anything. It uses an infrared light to measure the absorbance of formaldehyde. And so it's just measuring how much infrared light doesn't make it to the detector. The absorption is pretty small, so it samples clean air and ambient air. It switches between the two every, I think, 30 seconds or so. And then it measures the difference between the clean air and the ambient air to get the concentration. And it's nice to have these two instruments because the methods are so different that when the instruments measurements agree with each other, it gives us a lot more confidence with the data. It's also good to just have a backup instrument in case one doesn't work, which can happen a lot in the field. Yeah, that's all I have.
Very much, James. So the next person who's going to talk about ions in the particles. And this is Michael Battaglia, who's from Georgia Tech.
Great, thank you, Bill. So as you said, I'm Mike Battaglia. I am a postdoc researcher at Georgia Tech. And what you're seeing on the screen right now, we have three of those gray boxes. Those are called ion chromatographs. And effectively what they do is they separate ions based on how they stick onto a column. And so you've probably heard of things of like sulfate, chloride. We can measure and get a sense of what they are in the air. And we do this using two different collection methods. You can see kind of in the center left of the screen there on that ring stand with a syringe pump is a mist chamber. And as Jingchu zooms in, there's a syringe pump that moves our liquid. And what this is a mist chamber. And we can actually sample, this is not size resolved, and it is sampling gases and particles, anything that's water soluble. So that's your ammonium sulfate, that's your sodium chloride, your sulfur dioxide gas, things like that. We can sample into that water and send it to our ion chromatographs and measure those ions. And then further down the bench, we have a similar instrument, but it is only for particles. That's what you're seeing right here at the end of the bench. There is the particle into liquid sampler, or the PILS. And what this does is it samples only particles, and it samples them into a supersaturated steam environment. And then we can recreate, or we can use the same measurement methods here with the ions. I don't know if you can get a zoom in on the screen there, but basically we have these long time series measurements. And anytime an ion comes through this conductivity detector, it spikes, and we can measure the area, and we can know how much is in the air. So it's kind of hard to see, but yeah, we get these kind of like mountain looking things there. And so my group is mostly interested in, we want to look at effectively at the end of the day, aerosol pH. That's kind of my area of interest. And we want to see what that's doing to the aerosol chemistry up here. We don't know if it's quite as acidic as it is. I'm from the Southeast US, so We'll see how it changes up here, kind of in the cold and the dark. So that's kind of the brief rundown of the main instruments that I'm running here.
Okay, thanks, Mike. So the next person to speak is going to be Emily Pill, who's from Colorado State University, and she is going to talk about particles that form clouds.
Yeah, so hi, I am Emily Lill. I'm a graduate student at Colorado State University. And the goal of our research here is to look at combustion products do in order to form ice fogs. So what instrument is up right now is our continuous flow diffusion chamber, a CFDC, which basically pulls in particles from the air outside of the trailer and puts them through conditions that form clouds. So we can see what exactly is contributing to the ice fog here. We also, next to it, we have a drum sampler, which sorts. We also have outside, we have a X-ray fluorescent air quality spectrometer, an XRF, which measures total particle mass concentrations, as well as the specific elements that we are. And we also, out there too, I think she's getting there. I know, but it's going on a long walk. We have some filtered unit samples on top as well for offline sampling. We will take back to Colorado and look at these ice nucleating particles that form the ice fog here.
Great, thanks, Emily. And I know a lot of people are really interested in ice fog, so you might get some questions. So the next person who's going to talk is going to be Mita Sessler-Maloney, who's a graduate student here at UAF, and she's going to be talking about gas measurements and also temperature inversions.
Thanks, Bill. So what you're seeing on this screen right now that Jinshu's showing are our thermo scientific gas analyzers. So here we measure trace gases like sulfur dioxide, which is emitted from heating oil and as well as coal, carbon monoxide, which can come from lots of combustion, including wood smoke, the nitrogen oxides that come out of car exhaust, as well as ozone. And so these are nice support measurements for other people, people who are interested in the chemistry of those secondary aerosol formation processes, might be interested in the gas data along with the particle data. And then I will share my screen real quick to talk about the temperature measurements. So if you can see my screen now, we also have some temperature measurements at the CTC building. So the yellow star is temperature and wind speed and wind direction we have on the roof. And then the green one in the parking lot, we have a trailer in the parking lot that also measures a gradient of the temperatures. So here's just a picture of that trailer. If you've been around CTC, you've probably seen it in the parking lot. Now it has a lot more snow around it, but it's still there. And then we also have the temperature probe on the roof. We also have CO2 at both altitudes to kind of get a handle of how much the pollutants are mixing vertically. And then just to give you a quick look at these inversions, you can see that on February 3rd, we had a pretty strong inversion where the temperature at 23 meters was a lot warmer actually than the temperature near the ground. And then you can see that as the day went on, they eventually came back up and the inversion broke. So in these inversion periods are when we definitely see a lot of that pollution at the ground level. And that is all I have.
Thank you so much. So the next person to speak is going to be Ursula, and she is going to be telling us about sulfur isotopes in particles.
Awesome. Thanks, everyone. It's so exciting to see what everyone is working on. So thanks for sharing. I'm really excited to be here. My name is Ursula, and I'm a third-year PhD student at the University of Washington in Seattle. And I'm supporting a project to analyze sulfate particles using a high-volume aerosol sampler, which maybe Jinshu will show in a second, hopefully. But basically, a high-volume aerosol sampler is like a big vacuum cleaner almost, in that it sucks a lot of the air from the surrounding area And as the air passes through these filters, the particles in the air get trapped on the filters. So we have 5 filters for 5 different particle sizes. And so far, we've learned that Fairbanks mostly has particles that are 1 micron in size, which is really small. It's about 1,000th of a millimeter. And our plan is to analyze the sulfate in the particles. So sulfate is about 20% of the particles. And as you probably know, sulfate is 1 sulfur atom attached to 4 oxygen atoms. And so our plan is to analyze the isotopes of sulfur and oxygen in the sulfate. And that will hopefully tell us where the sulfate is coming from and what steps we can take to most effectively reduce the sulfate amount in Fairbanks. Thanks.
Thank you. Okay, the next person to speak is going to be Sarah, and she's going to tell us about some other isotope measurements in both gases and particles.
Yes, hello. Yeah, you hear me? Yeah.
Yep.
Hello everyone. So I'm Sarah Albertin. I'm a third-year PhD student in France in LATMOS and IG laboratories. I don't know if Jingxu is going to go outside to show the instruments. But
there are 2 mooses outside. There are 2 mooses outside. It's kind of
okay.
2 big ones. So we
oh yes, there are mooses outside. Yeah.
So I try to stay.
They are here for the show, I guess.
That's right.
Okay, so so basically we are kind of using the same method as Ursula. So we also have a high vol, but we are not looking at sulfate, but we are looking at nitrate. And so we also measure isotopes in nitrate. And maybe I can share my screen just to show you a brief presentation, as maybe you can see. So yes, we use isotope to trace the nitrogen cycle in the atmosphere. So from the emission of NOx to the formation of particulate nitrate. And so basically we sample NO2, so it's an intermediate in the NOx conversion into nitrate on the denuder tube. And we also collect nitrate on filters. And then we extract these 2 sample materials and we measure the stable isotope distribution, which give us information about the chemistry processes and also to trace back the NOx emission sources. And that's it for me. Thank you for listening.
Thank you. So the next person will be Brice, and Brice will be telling us about real-time particle and gas measurements here in the Gold Trailer.
Yeah, so hello. Can you hear me fine?
We can hear you.
Yeah, okay. So this is the Gold Trailer, where we have installed our instrumentation for the real-time analysis of the particles and the VOCs. So I will just shortly show you the AMS for the particle mass composition and also the VOCs. So if we go inside, we can see this guy. Yeah. So this is the mass spectrometer, the AMS. So it's designed to analyze the particle phase on real time. So just to remember, the particle we analyze below 1 micrometer. So it's 60 times less than the diameter of a hair, just to see. And what we can see here is a kind of a time series of the different components that the aerosol mass spectrometer can measure in the same times, which are sulfate, nitrates, organic, chlorides, and ammonium. So what we can see here, just try to make a zoom on the last 24 hours of measurement to see the kind of performances that you can see, that you can get with this instrument. So you can get very low concentrations and you can capture very fast variations of particle concentrations. And its trend, the same, but it's dedicated to measure the VOCs. So VOCs are like toluene, benzene, gas phase molecules that are also in the air and are emitted by the different sources. So this is this instrument here. It's a PTRMS. And so just to show you also the time series that we can get here. I don't know if you can see it clearly. Yeah, maybe it's not so easy, but what's it's getting, I mean, you can get 1 point every 20 seconds of measurement of VOCs at ppb level. That means less than 1 molecule per 10 power 9 molecule of air. So, and also, we have also a very nice time resolution. So every 20 seconds, we have a measurement. This means that we can also capture even cars passing by the roadside near the CTC sites. So that's it for the whole trailer.
Excellent. Thank you very much for showing us and also showing how loud it can be in these trailers. If people could hear, there's pumps going on, there's all kinds of things going on, maybe alarms going off. So, all right. So the next person to speak is going to be our last, and that is going to be Jochen Stutz, who's going to be talking about vertical profiling with light.
Hi, good evening. I'm Jochen Stutz. I'm with the University of California, Los Angeles. And I'm actually showing slides because our instrument is not at the CTC side, and it will become obvious why in a moment. What we're really interested in is this idea that Jinshu and also Mita addressed is where is the pollution in Fairbanks in the vertical? So we already heard about surface inversions. And one of the challenges in figuring this out is that it's really hard to access anything that is above the rooftop level unless you have like really high towers, or you have a balloon that you tether, you can't fly airplanes that low. And this is where we're coming in with this instrument. We call this long path differential optical absorption spectrometer because nobody really wants to ever say this. We call it LPDOAS. And in short, what it is, it's a telescope, fairly large telescope. And as you can see in the bottom picture here, just to give you an idea, the main mirror is about 1 foot diameter. And that telescope shoots a beam of white light. And that sounds very sophisticated, but it's actually not very strong light. It's about the kind of strength of a car high beam. And we make this very parallel and we shoot it through the atmosphere. And then we hit an array of fancy cat eyes, which you can see here on the right. And this is actually in Fairbanks at Birch Hill. And Bill Simpson heroically skied those out into the middle of the hill and set them up a few weeks ago. And so these cat eyes basically reflect the light back, that we catch it, and then we can analyze it to learn something about pollution. And so in the center here, you see actually a light beam. This is not from Fairbanks. We actually use some color filters so that people can't see the light beam. The pilots that fly around Fairbanks appreciate that. So now with this instrument, you ask yourself, how can we probe air masses that are away from the surface? And we do this, if you look at the top figure here, is by mounting these reflectors alongside Birch Hill. So the top one is about 200 meters, so about 600 feet above the surface. And then we aim this telescope at different altitudes. And by that, we can then get information what is up in the air above Fairbanks. And we do this sequentially. On the bottom, you can see actually a view, and I made these reflections a little bit bigger so you can see where these reflectors are in Fairbanks. And we just aim one after the other, and then we can learn something about what air pollution is. The lowest path actually is fairly low and compares very well to some of the things CTC sees. That's on purpose because we want to have the ability to compare. And because I can, I'll show you one of the results, because obviously we were really curious what happens. And so when we compare two of these paths and we just look at pollution levels, you can see that the pollution levels in the lowest, about 20 meters, 60 feet, are about 5 times larger than what is above 20 meters or 60 feet, which is kind of up here. So I labeled this here a little bit just to visualize it. And this is during the period about, a week ago, this very cold, very calm period where we had these very strong surface inversions. And what that basically tells us is that these temperature inversions that you get in Fairbanks really help in driving the pollution levels up in the atmosphere. And unfortunately, we all live in those lowest 20 meters, so we get exposed to these high levels. And our interest really is to understand how this changes in the vertical. Thanks for listening. And if you have any questions, I think we're transitioning to the question period, right? Thanks, Bill.
Yes, we are. Thanks so much, Jochen. And thanks to all the presenters. That was really quite a whirlwind of measurements. And you can, I think, get a feel for the state-of-the-art measurements that we have here. It's a really exciting project for us because this is much more detailed than we've had in the past in the prior measurements. And a lot of it's coming in much faster, minute time resolutions instead of hours or days. And that helps us to separate out things like influence of specific sources like individual cars or badly emitting truck or something like that. So we can really get a huge amount more information with this type of measurement. So that was our description of the instruments. I think I might invite the people who talked to maybe put a little reminder of what measurement they make into the chat so that if people had questions for them, they could direct a question to a person. I think you could also ask any of us to direct a question to one of the speakers. So with that, let's hear questions from the audience. I think you can type questions into the chat. People on Facebook can also type in comments, and then those will be relayed to us by some people who are watching the comments over on Facebook. Yeah, so Kelly's doing that. Additionally, I think the people on Zoom I think they're able to unmute and ask questions if they'd like.
Bill, this is Mike Kraft. I was just curious about the elevations up at the university of the two units, the one on the roof and the one in the parking lot, if you had an idea of what those elevations were.
I think Mita, you could talk about the heights of the sampling set.
Yeah, so in the parking lot on that tower and the little white trailer, those are temperature measurements at 3, 6, and 11 meters. And then the roof, we think, is about 23 meters tall.
I was referring to like elevation above sea level.
Oh, above sea level, I guess it would be like the roof would be about 155 meters because Fairbanks is about 135 meters above sea level. So from about 138 to 155 or 158.
Most of the heights we measure are off the valley floor because the way the cold air pools in these inversion events, it goes down to essentially the river level, the valley floor.
Right, that's why I was asking the question. I noticed they were both up on the hill at the university, and I can drive off my house about 200 feet above the valley and be at say 30 degrees or 20 degrees and see minus 15 in the valley. So big difference. That's down along Tina Pump.
Yeah, and so they're both at the CTC building downtown. So they're kind of on
604 Barnett, which is the old.
Okay. That makes sense now. Thank
courthouse.
You. That makes sense. Thank you.
Yeah, in fact, the university is something like 50 meters above the valley floor and typically is in pretty clean air compared to what you'll have down at the valley floor.
Thank you.
It's a great question. So other questions from the audience?
This is Liz. How you doing?
Good. How are you doing, Liz?
Thank you for all your work. I'm beginning to appreciate your efforts more and more. I've lived here for 30 winters, and I've heard a lot of stuff over the years about inversions, pollution levels, air quality, particle sizes. I'd like to have kind of an idea from the group, if I could get it, how you felt this study impacted you, and had any of you been to Fairbanks before? And if you hadn't, what did you think of it? And what did you think of the condition, your working conditions?
It's cold. I would say that. I didn't say this, but our instrument is actually in a tent in an open parking garage. So we actually work at ambient temperatures. We do work, and I can tell you it is very cold. But on the other hand, I'm from LA, so I'm actually enjoying the winter.
I see Jack's hand up. Maybe
Yeah,
we'll
I mean, I have been to Fairbanks before, and probably never quite this cold in Fairbanks. I've been here in April before. But with many of the people on this call, I've spent a lot of time in really cold places like Summit, Greenland, and South Pole. So it's not that cold here. And it's not as dirty as some of the places I've been either. But it's impressively dirty sometimes, as Jochen was showing that period right at the end of January, beginning of February. It was impressively dirty for a few days, but not like Houston, right? I mean, heavens. Sorry, Jimmy, if he's on.
I might just go around a couple more of the participants because I think this is a really interesting question. So yeah, let's do Vanessa. And then could I hear from somebody from another country, European?
Hey, Liz, I really appreciate your question. I typically, or what our group typically primarily does, we do a lot of wildfire smoke measurements in Montana in the summertime. So this is quite different to what we're typically used to. I personally love the cold. I don't ever want it to not be winter. I would be really happy if it were winter all the time. So I'm having a fantastic time here in Fairbanks. But in terms of the science, it's been, as somebody who recently graduated in the last couple of years, it's been really, really cool and interesting to see how different the environments are. And kind of, despite the differences in the environment, I think that our main priority, whether we're sampling, stuff in Montana or whether we're sampling in Fairbanks, is to really be transparent with the community as well about what it is that we're doing and how our science can help make your life easier and hopefully better. So I think the other important thing to note too is that this community has been fantastic for that kind of stuff as well. And it's just been wonderful to be here. And again, I just really want to thank everybody in Fairbanks for having us here and allowing us to do this study and coming at it with enthusiasm and an open mind. We appreciate that. Thanks.
Yeah, thanks very much. Is there a person from, we don't have the Brazilian on this call. We have one person who was from Brazil who was working at the house. I don't know who's the warmest European.
Say, go on, Grace. But it's not really working outside.
Well, I don't know if you, can you hear me?
Yes.
Okay, so I'm from France, not from the warmer place in France. I'm come from the mountain, so in the Alps, from Grenoble. And I have to say that it is actually the coldest place I ever been here in Fairbanks. So for me, it's very cold, and it makes things a bit harder, I guess. Sometimes, but so yes, no, for us it's a kind of hard condition, even if we don't spend a lot of time outside. But I have to say that for me, it's not the problem is not the cold, maybe it's the lack of sun. It's more this thing that sometimes you just want the sun to heat and it's too warm and it's not warming. It's here, but it's not warming. So it's maybe the thing I miss the most. But yes, for us, a European, at least it's very different condition from what, even if we come from the Alps, it's not that cold in winter for sure. So it's very different from what we are living usually in wintertime in Europe.
Thank you. So maybe we could go to Luke Hopkins, who has his hand up, and then Mike after.
Yeah. Thank you very much, Mr. Simpson. If I can call you Bill, that's okay. I've been here for about 55 years, been an elected official who's had to deal with the air quality planning and reactions to it with the local government, and interacting with both federal EPA and the state DEC. I'm trying to come up with a plan. So the monitoring station that is down by the old courthouse, that the picture is, and some of the discussion, and I may have missed some of the pertinent discussions, but two things. Is this monitoring station adequate to get a sample, or with other samples to get a valid composite measurement of the particulates from the traffic component of both car and truck exhaust? And I brought this up in a recent Zoom, is we're anticipating in a few years the possibility of very, very heavy diesel truck traffic coming through a consistent route where this monitor is not located. And it's true, we could probably establish another one, but this is kind of a firm or well-established and legal location possibly. But I am concerned that we may not be sampling the particulates from this heavy truck traffic that is going to be possibly as many as 192 trips a day through the airshed that is in the non-attainment area. So I just wonder about that, and what might be the sense of these experts. And I thank you for coming here to Fairbanks and all the work that you're doing in both the cold and snowy environment. So I look forward to hearing some comments if you're able to do that, if this is a relevant question, which I hope it is. Thank you.
So just to say a little bit about the study here, is that this is a really focused, somewhat short-term study. So the site will go through the end of this month, but it won't be operational when those big trucks come through for that mining project. So unfortunately, we won't capture that. But on the other hand, we do have these real-time measurements. So maybe I could ask PTR or AMS, maybe Brice could talk a little bit about ways that your very detailed measurements can get at different types of emission sources.
Yeah, because you're measuring a large amount of VOCs. So first, you can have different fingerprints from different sources. And the second point, because you're measuring with a very high time resolution, you can also have, you can capture like a car passing by, or so you can also have this fingerprint thanks to the very high resolution. Yeah.
So just in the past studies, the state office building, you'll remember, is across the street from here. And the state office building used to be where we monitored the pollution downtown. And it was mostly done by 24-hour filter samples, very, very long-term averages. The type of things that Brice gets is essentially minute time resolution with similar, actually better information about the chemical compounds that are there. So you can look at specific tracers of certain emission sources. A chemical called levoglucosan is a dehydrated sugar that comes from wood smoke. So it's very specific. There are compounds that are specific to other automotive or diesel sources. So I think we're going to get a lot more information along those directions from this study in terms of what emissions trucks are putting into this area. And a very fascinating thing that's good here is being at the downtown site, you have more cars and trucks coming by, and we can compare to similar measurements at the house, which is in a residential area. so we can look at the difference between these two sites and hopefully get some insights into residential sources versus, say, downtown transportation sources. There's a couple things in the chat that I'll refer people to, but I do see a couple hands up. So I think we should go to Mike and then Liz, and Jochen, if you have something related to this, maybe you could type it in the chat because we've only got a few minutes left.
Thank you, Bill. I was really interested in the snow collection sampling that was referred to earlier. And I'm just kind of curious if anyone has done any of that sampling down along Phillips Field Road, where we have this artificial ice fog that develops as a result of wastewater from the steam plant that's being put into the river and pretty much builds its own plume for about 1.5 miles. And at some points in time gets heavy enough to where it actually coats Phillips Field Road to the point to where it's very slippery. And I'm just curious if anybody has thought of how that might play into some of this too. If that ice fog does capture this stuff and put it on the ground and then release it later, like he was talking about. Just kind of curious about that.
So Mike, this is Jack, and I've not really done a gradient along Phillips Field Road, but the site where we sample, the Encore site, is in between the Borough Building and the Elks Lodge. So very close to the power plant.
Yeah, you're upstream from it.
Sometimes I've seen that stuff, coming towards me, and definitely the stack plume, it goes overhead a lot of the time. But I have driven through there. And so, I mean, I have not gone and tried to intentionally sample where that stuff is depositing a lot. I don't know. It might be very interesting. I would think it would be pretty clean because it's so much fresh steam. But you're right. Anything that was between the point where it was emitted and the ground might get washed out by that steam. And I have done a little bit of collaborative sampling. Most of my sampling has been at that Encore site, which is the one I just mentioned by the Elks Lodge and the Borough Building. But I've sampled a few times at Farm Field site where the Helikite, the balloon team, has been working, and a student collaborator collected a bunch of samples in North Pole, and she's supposed to do that again this coming weekend, and it was quite different. The snow in downtown Fairbanks looked different in some regards from North Pole, and be interesting to see if that maintains itself over this next sampling period that she's going to execute in a few days.
Well, I hate to brag to you guys, but for some reason I did the math at one point in time, and after 41 years of living in Fairbanks, I figured I had 7.5 years at -30 or colder working outside. just to throw that out there. That's why I look the way I look, I imagine.
Yeah, I don't know if you scale it for even colder. And I spent with many of the people on this call about 6 years in aggregate over 20 years at Summit Greenland. And it was often colder than -30 and sometimes as cold as -60. That's not that much fun. And South Pole is even worse, but we won't go there.
Right. So thanks so much for the question. And let's go to Liz.
Thank you very much. I appreciate it. I typed it into the chat, but I wanted to know, as Luke brought up, we're supposed to have a massive number of trucks coming through town as a result of development at mines. And I'm wondering, A, if you can come back and measure this, and B, if you can you leave some suggestion to UAF on how to measure it the way you're measuring things right now? Is that possible?
That's a good question. And thinking about if the very high resolution measurements that are being done both in time and chemical detail might give a real signature that one could look for. I think it's something we could think about based upon, say, Breese's measurements. These instruments, I should say, these instruments, the reason that we do these measurements in field studies like this somewhat short term, a couple months, is that you really can't do these measurements long term. It's just too much work. So the routine monitoring is done by other methods, and we collaborate with the Alaska Department of Environmental Conservation, who does that hard long-term measurements. And those are, of course, the regulatory measurements. The measurements we're making are not regulatory measurements. They're trying to understand chemical processes, not legally binding or anything. So we're trying to put a firm scientific underpinning under the things that are the regulatory questions. So,
and I just quickly interject, because that also is something you've been doing. You've been building PM 2.5 sensors in schools. And there is actually this Purple Air network, and we bought some of these sensors. So there's actually, I don't know if you've ever been on that website. So I mean, I could tell you from Los Angeles, when we had fires here, people don't look at the regulatory websites anymore. They all look at Purple Air to see where the smoke is, right? Because the density of these sensors is just, it's amazing what you can see. I mean, you can see plumes from fires basically just cutting through a city, and you can see exactly where these are. So I think this is an awesome modern tool, and I think Bill's already getting kids involved and schools involved, and I think that's a great way of engaging the community and also providing data that even we couldn't do because we can't be everywhere, right?
Yeah, so what Joachin's talking about is middle school students built 80. The students in Tanana Middle School actually built 80 small sensors that they could bring home and measure pollution inside their house. They could make toast or things like that to try and understand indoor sources in addition to outdoor sources. And the students are now doing their own design by themselves scientific inquiries into particles. And we'd love to do more things like that in the future too, to just raise awareness. Because I think one of the things about wildfire is you see these dense plumes and you know that it's unhealthy. Because the pollution is so shallow in Fairbanks, it's hard to see the pollution like you can see it in a giant, thick smoke plume. And it's still there. It's at similar levels to what it can be in wildfire smoke days. But it's just harder to see, so people forget about it, unfortunately. Thought I saw a hand up.
Oh, I was just going to add to your comment, Bill. I think those are great questions. How we can get, how can we come back and do more of these studies when there are other pollution events? And I think really Bill made a fantastic point about just getting the awareness out there. I had a conversation with my mom yesterday about climate change and showed her a couple of infographics that she wasn't even aware of, or she didn't even know existed. So I mean, the first step is obviously coming to things like this, which you've already done. And that's fantastic. And just tell more people in your community about these kinds of events and what they should be aware of and the pollution that they should be aware of. And eventually they'll start to get interested.
Yeah, thanks, Vanessa. And actually, that does point out that we intend to take some of the results from this study and try to make informative infographics, things that will be things that answer community questions like we've talked about. So that's in our long-term plan of things that we're going to do. And we really, really appreciate the community's coming to this event and being a part of this project, and keep asking questions and looking for our continued involvement in this, bringing back what we're finding and trying to help people to clean up the air here.
Bill, how would a person get a hold of some of your end of line results? You know, when you guys are all wrapped up, is there going to be an opportunity for the public to review some of this data that you guys are compiling?
Yes, so we'll be bringing it back to the community. So we're going to have, after this, a kind of data meeting. This was what usually happens. And then we're going to kind of pick some of the parts that we really feel answer community questions, and then have public talks on those results. So that's our plan after this. It's going to be about a year before we're back to talking to the community. So look for that next winter.
Any chance you would consider publishing a graphic novel? Sometimes that gets people's attention a little bit more than a dry report.
Jack, can you talk to your colleague? One of Jack Dibb's colleagues, I think, makes graphic novels.
We can look into it. I think there's some pretty, you could come up with some pretty compelling visuals. It wouldn't be that hard to tell the story.
Yeah. Or maybe
On
one
the, Bill, if I may, one of our dear friends was an elementary school teacher in downtown school, and she got I think she got a national science grant to do an air monitoring experiment in the classroom, and they basically just took a vacuum cleaner and put a high-level filter on the end of the hose and stuck it out the window for a period of time, and then brought it in. And of course, it was really soot-laden just in the downtown area. And then they looked at it under microscopes and things like that. And the kids were also really impressed and going, "Oh my gosh, this is what we're breathing." So it was an excellent demonstration for elementary school children to understand when they can just see the air quality issue right there on the filter. Thanks.
Yep, definitely. There's a lot of power in that. Thanks. So Jack, and I think we're about 2 minutes over time, so I think we should wrap it up with kind of final comments here.
I was just going to follow up on Luke's comment. I've been really amazed at this NCORE site to look at the amount of nasty black particles that you can visibly see in the snow. So I remember when I was a kid, we used to always eat the snow. I would not let my kids eat downtown Fairbanks snow. And that's easy. You could just take a scoop of snow and melt it, and you'll be amazed that they're big. They're big chunks. You shouldn't be able to see these aerosols everyone else is talking about, but this is some pretty big hunks of something from who knows what, but trucks or the power plants or a combination of everything. But every day I have to filter my samples before I can even analyze them because
yeah. All right. So thanks so much for everybody who was involved here. We really appreciate your involvement. And what we're going to do from here is on the Fair Air website, fairair.community.uf.edu, we will put up a video recording of this. It may take a little while, a week or so after, but you can send other people to take a look at it. If there were any questions in the chat that didn't get answered, we'll look through there and we'll post those. So yeah, thanks Vanessa for putting up the link there. So with that, I want to thank everybody, thank all the presenters, and thank all the community folks who are here. So have a great night.
Thank you again for coming.
Thanks for having us.